got three interesting papers coming up. One by Gordon Allen from Heriot-Watt University, one by Professor Ray Harwood from De Montfort University, and one by Dr. Aisha Oman El-Breki from Libya. Gordon Allen will present the first paper. Gordon has a degree in chemistry and management from Edinburgh University, and he's been working applying neural networks to simulation and prediction problems in textiles in areas including polypropylene melt spinning, plasma treatment and fibre identification. His current interests focus on process optimization systems and the use of neuro-fuzzy logic systems. Gordon, please.
Thank you very much. Thank you, Mr. Chairman. Thank you, Mr. Chairman. Thank you, the Textile Institute, for inviting me to speak at this conference. I'm just going to bring up my presentation. I'm just going to start it displaying. Now, the work that I've been undertaking was to use certain AI tools, namely neural networks and fuzzy logic adaptive fuzzy logic systems, to tackle the difficult problem of identification of certain natural fibres, namely animal fibres, cashmere and lambswool, although it could be extended because of a similar chemistry to any other animal fibres. I don't know if you can make this out very clearly. You should be able to. The two of you should be able to make this out. Can you read that? Yeah. Good. And it's actually an extract from the Scotsman newspaper last summer, when a local cashmere knitwear producer in Hoyt, which is a town near my town, Galashiels, faced near disaster when their big American customers discovered, or appeared to discover, that although the garments were labelled 100% cashmere, they actually contained about 95–96% cashmere, because someone had sent them to a watchdog, a quality watchdog, called the Federal Trade Commission, and the Commission had sent them to a renowned textile analyst called Professor Langley, who some of you may know, and it was reported that it had this less than 100% content. Sorry, a little louder? Okay, sorry. It's quite, I think I'll hold this. Okay, I'll do that. Now, I'll just point to certain. I've talked about the discovery by the independent watchdog. There could be compensation claims, so these problems of labelling, apparent mislabelling, claimed mislabelling, can lead to litigation problems. And of course, in the States, that can be very costly. That if a retailer was marketing the products from this company with a label saying 100%, they could be sued for damages. Nightmare, serious embarrassment. In fact, they had to hurriedly relabel their garments saying at least 95% cashmere. And they just about got away with it, but they've since been sold. That company never recovered fully from that position. That's just another extract from the Scotsman. Widespread implications for the whole Scottish cashmere industry. That employs thousands of people in the south of Scotland, also up in some in the north of Scotland. There are also cashmere-related companies in the north of England, and all these companies would be affected, and quite a number of people would be put out of work. So there's a call. That was one of the boss of Clan Douglas, the company concerned. We need a uniform system to test cashmere to eradicate future confusion. if you go to 4 different testing labs, now there are commercial labs around the world for analysing animal hair content, you get 4 different results. There is a definite amount of variation when they do round trials of these labs. So what we need is not a subjective process which uses a lot of human judgment and the microscope, we want an objective analysis system. We did a small survey as part of the justification for this project, and we found that all the producers were deeply cynical and suspicious of the test system as it stands. They didn't like the sort of reports that were coming through. They knew that they had good products and good materials, but sometimes the results of the test seemed a bit challenging. This was a very serious embarrassment for the whole industry, and the pressure is now on to find a better test system. And when I go back home, within a few weeks I'll be demonstrating my software, the finished, a demo version of the software, to a group of textile, of cashmere producers in Scotland. When China joins the whole market in 2005, there'll be even more pressure on corporate quality control and standardization on these high-value quality goods, these cashmere knitwears. The problem, of course, is that very small differences in the chemistry. Cashmere and lambswool, it's keratin protein, it's a mixture of peptides linked together. The differences are in minute structures, but we don't have a straightforward objective test to analyse these minute structures. I mean, you can do electron microscopy and so on, SEM, but you can't do SEM all that easily in a routine mode in a quality lab. Very small chemical differences. People have tried in the past to differentiate them on the basis of chromatography, electrophoresis, breaking down amino acids, even using automated systems, but the results have not been conclusive and reliable. Physical differences: cashmere hairs tend to have smaller diameter, but there can also be overlaps in the diameter distributions. They tend to be smoother and less stepwise down the fibre length, but even then there can be overlap fibres. There can be fibres that you cannot tell by looking at them exactly which class they belong to. There could be visually, by inspection, you can see great similarities often between cashmere fibres and fine lambswool fibres like merino. The current standard test involves analysis of fibre lengths and diameters, which may not be conclusive. It would probably indicate that there's more than one population present. It might not indicate exactly what kind of populations these are. Solubility testing can indicate the integrity of the fibres, whether they're recycled, whether they've been pre-treated and so on, or made to look like something that they're not. You can do solubility tests, but the main critical one is when an expert looks through the projection microscope and looks at the individual hairs. Now I've fiddled around with these images to make them look as if they were more or less the same sort of diameter. But one is the merino scaling for a particular hair, and then there's the cashmere scaling for a particular hair. You can see that they could be seen to be completely different, completely the same to the unexperienced eye. And even to the experienced eye, there could be overlaps. There could be sections of this hair where the patterns are actually merino patterns. There could be sections of this hair where the patterns are cashmere patterns. And of course, this is only one hair out of thousands and millions in a sample. DNA, of course, would be definitive. We could say, yes, genetically, that is from a goat, it is cashmere. Genetically, this is from a sheep, this is lambswool. But DNA, although it is offered as a test by this British lab, BTTG, and is backed up by the CCMI, the Cashmere and Camlin Manufacturers Institute for the US, they're actually working very much in Europe now. They see the importance of having a European presence, and they've also taken quite an interest in my work, and they'll be having more contact with their representative quite soon. Yes, you could do DNA testing, but DNA testing will never be a particularly straightforward and ready-made quick kit type test. And also there's always the threat of contamination. It's one little eyebrow. You'd have to have genetically, people experienced in biomedical genetic type laboratory work, not just the usual textile technician. So we need an objective system. We could get away from the reliance on experts, reliance on picking out a few hundred hairs from thousands and thousands of hairs. We need a system that could handle different finishes. Because once you start looking through the microscope, if there's been red dye stuff, blue dye stuff, a pattern mixture, a felting or whatever, then this can confuse the whole microscopic examination. The basic approach that I used was to use a ready-made and established instrumental method, FTIR, infrared spectroscopy. I use attenuated reflectance approach, and I get very low noise spectral data of high consistency. I use special normalization processes on the data. I extract optimized subset frequency absorbances, and on that basis I get reproducible data sets that represent the samples. These data sets are input to a learning system that uses so-called neural networks, and there it is. Neural networks are, I'm not going to spend a long time explaining, a lot of people have already introduced neural networks over the years now in many textile applications, basically mimicking the human brain in adapting to situations and learning to please us by mapping inputs to target outputs. So you can have models, you can have simulations. Coupling that with fuzzy logic. Now you may say, well, why use both at the same time? You could have used one and compared it with the other. But the advantage of the fuzzy logic is that it produces explicit rules. And of course we can then supply these explicit rules to anyone who wants an explanation of the classification carried out by the system. That's just an example of the sort of spectrum that you would get from a piece of white Chinese cashmere with no finish applied to it. The fun, the joy for me was that even if you do dye it, the dyeing only affects certain frequencies, not many. And the quantity of the dye stuff is so small in proportion to the quantity available of the fibre that it does not present too difficult a problem for the classification. So it doesn't matter whether it's blue cashmere, red cashmere, yellow cashmere. It doesn't matter too much. This looks a bit stepwise and a bit lumpy, but in reality there is very low noise. The only noise I would expect would be in the higher frequencies up at that end. That's a characteristic of the type of data gathering system I'm using. It's basically AI, because how much time have I got? 5. Using machines to impart intelligence, using computers, and our desktop computers are very powerful, pretty fast nowadays. You can give them terrible things to do and they manage it in a few seconds. And so yes, we can get them to copy our learning capability. We can get them to copy our ability to recognize relationships. And if we apply AI to situations like the fibres analysis, it means we don't have to employ expert fibre specialists quite so much, and we don't have to back them up when we go on holiday, and so on. I want to just show you first of all, now there's one thing about neural networks is they're only as good as the data they were trained on. And the data has to be good enough, it has to be quality data, it has to be good enough to solve the problem that you've got. And one way to look at the quality of the data is using a particular type of neural network that I really appreciate, and it's the Cohonen self-organizing map. And this is a particular type of learning system where you don't tell it about any correct answers. You just give it the data. You do your best to gather the data in a balanced way, so it is representational of the global population of samples. But then you feed it into this map, a neural network that learns relationships. On all it doesn't know anything about cashmere and lambswool, but what it will do is do a nearest neighbour reshuffle of all the samples. So if it sees things as being similar to each other, it will move them together. And if it sees things being similar to something quite different but to each other, there'll be another cluster that will move down to another part of the map. If you cannot form a meaningful map of your data, then you cannot train a neural network to form boundaries between the clusters. Now I hope you can, unfortunately some of these things are similar colours, but there are only 3 important colours here, or 4. The yellow, now the Cohonen map pushed these samples, like sample number 33, sample number 15, it pushed them into this 2-dimensional representation. Now the data sets were at least 12 values long, so there are 12 dimensions of data involved, but the Cohonen always gives you 2, which is a very useful trick. And thankfully, it was found that the cashmere, a lot of the cashmeres formed their own family, their own cluster up in that corner. And a boundary, now to drawing a boundary, I like using the pen. Drawing a boundary would be not difficult, would it? You could do that. And then if you wanted, yeah, you could do that. And you could separate sections. Those 2 samples there, that was quite interesting. Somebody started to send me Escorial. It's a speciality wool from New Zealand, yes. This is New Zealand trying to produce exotic products to rival Mongolian cashmere, yes, and give it high value added. I was very relieved to find that my system actually placed them together and saw them as different from other types of lambswool, which was interesting. Obviously just 2 there, but I think that it shows that there's potential for a system that will actually identify Escorial as another class of animal fibre, which is quite interesting. And then continuing our little boundaries, there could be a cluster down there. Here's a section of lambswools. Now, it's not perfect, but I hope you appreciate that there are areas where it sees similarities. Now, more work needs to be done as to why it should have separated those lambswools from those lambswools, except that now I'm checking my colours, the merinos are there, and the geelongs, the blue geelong, are there. And that was another interesting fact, that the geelongs were still being placed beside geelongs. So I was wrong with that line. That one belongs through there. So you see the data was doing pretty well for the boundary forming problem. I hope you appreciate that. And there is still 1 minute. Oh well, I better push on. I'll try to get away from my interruptions and move on. I haven't got much time to discuss the fuzzy sets here now. It's on the CD from the conference, and you're also welcome to email me or contact me if you want any discussion about using these systems. Basically, the fuzzy sets, there's an example of one of the inputs, one of the parameters used, and the system identifies meaningful ranges that it sees as being useful to the classification problem. Half sets, lost my little pointer now. Half sets, where you got down to that, there's full membership of there, zero membership there for that range of input. Zero membership, full membership, zero membership for that range of input. So it breaks each variable into meaningful ranges that correlate to ranges of the output. And then it produces meaningful explicit rules about if the absorbance at a certain frequency is in the range that we call low, and if the absorbance at the frequency 2 is high, and so on. So it gives you a combination of frequencies. Then it says, yes, it's cashmere, but I'll only give it 49% weighting there. It could just as well be lambswool. So it's not a very convinced rule there. And that wouldn't make much difference, of course, to the outcome. Yes, I'll just move swiftly to the sort of results I was getting. On the fibres that it was trained on, it was quite happy to show that it had formed its boundaries, and I used a confidence measurement that showed how easy it was to synthesize these from well-known examples. On blind tests, on so-called pure samples, not too bad, 8% error, 4% error, average over the piece 5%, and that was on the first 66 samples. Once the samples were up to 83, the average error was 3%, 3.6, which wasn't bad on samples that were not in the training set. And a sort of graphical presentation of that. No requirement for chemical skills, straightforward technician skills, rapid collection of data, so you can actually handle more samples and take more averages. And of course, when I put a piece of fabric or a piece of felt into my system, it's looking at thousands of hairs at a time. There's no problem about the sampling. The identification of the material, my system can learn to ignore the colour, ignore the finish, which I think is a very useful thing. And I can make it better just by expanding the database. It doesn't make assumptions or simplifications like mathematical models would make. We can retrain this to look at other fibres. We can look at cotton. We can look at cotton blends. We look at hemp. There's the demo program working. I put a sample in, and it says, okay, sample 1, cashmere. There's the crisp equivalence of the fuzzy logic model, very much into class 1, negative class 2, interpreted as 100 and 0. And if I ask for explanations, it's kept a memo of all the hits made by those rules, and I've related the memos back to the chemistry for those absorption bands. And so you can actually get a chemical signature with various levels of importance that define that particular sample. And I think more work can be done on this sort of signature. Quantitative blends. I haven't got my hands on enough blends that I know accurately. Yes, I'm finishing. I'm dying now, yes. I synthesized blends mathematically, and I got an average absolute error of 5%, which is not too bad at this stage of the graph. Continuous improvement, develop a test for general fibres, and I could use a hierarchy. I could say, what is this anyway? Okay, if it's that one or that one, what exactly is the blend? And we could do other quality tests. Okay. and I'll just wind it up there. Thank you very much for your attention.